All right, guys, so we're going to go over something called formal charges in this video. This will allow you to figure out, whether or not a Lewis structure is a good reflection of reality, even if it does follow the octet rule for all your non-hydrogen elements and the duet rule for hydrogen. Sometimes you can still have multiple Lewis structures that follow those rules, but one of those structures could be the most stable one, the best reflection of reality based on these formal charge rules. And so this ties into basically electronegativity. So remember that electronegativity is the ability for an element to attract electrons to itself in a compound. And that as you go to the right on the periodic table or up on the periodic table, electronegativity increases. So fluorine is the most electronegative element because it's on the top right. Francium is the least electronegative element because it's on the bottom left. Noble gases don't have electronegativity because they can't form compounds because they're happy being noble gases. Generally speaking, that's true. So electronegativity also, remember, told us something about what atom is in the center. And the most electropositive, the least electronegative element is going to be at the center. This kind of makes sense because really high electronegativity atoms don't want to share electrons. So they're going to want to be on the end where they can have more towards themselves. But if you're at the center, by the very nature of being in the center, you're sharing things with more people, electrons with more atoms, right? So that's why electropositive goes in the center. I'll give you this scale that's on your formula sheet. So I'll give that to you on the upcoming exams, exam 3 and the final. But that's just a reminder of this scale. Again, you see cesium at the bottom left here and fluorine at the top, ranging from 0.7 to 5. 0.7 to 4. So Lewis structures of polyatomics, we did some practice with that. Right, we were okay with that. We add brackets and then we added the overall charge. You can add a full brackets like shown here, or the half brackets that I did in the previous videos, just in the top right. That's fine. So let's go over the Lewis structure of CO2. We did this one as an example. We saw that it has 16 valence electrons. Carbon's the least electronegative, so it's going to be in the center. And we came up with this Lewis structure kind of naturally, what you would come up with most of the time, because it's very symmetric. You put a double on each. But we could have also come up with this one. Look, it also has an octet rule satisfied. 2, 4, 6, 8 for oxygen, 2, 4, 6, 8 for carbon, and this oxygen is 2, 4, 6, 8, right? 2 in the lone pair, 6 in the bond. So although it's looking a little less symmetric, it actually is totally a valid Lewis structure. So how do you know which one is really more correct or a better reflection of reality? So this is this idea of having multiple valid Lewis structures called resonance structures. I mentioned that before. And which one is more correct? So to figure this out, you're going to use something called formal charge. And basically, you're trying to figure out what how much the electrons are actually, where the electrons are on the atom, okay? So where the charge is distributed on the atom, okay? And so this is the formula for it. It's the number of valence electrons in the neutral atom minus the number of non-bonding electrons minus the number of bonding electrons divided by 2. So you think about, like, where does this come from? An element has a certain number of valence electrons intrinsically to it. Like carbon has 4, fluorine has 7, right? Sodium has 1, okay? And then you're going to subtract off the non-bonding electrons because those really aren't really doing anything, okay? And then you're also going to subtract off the bonding electrons divided by 2 because you're sharing the bond. So one of those counts and one of those doesn't count. So that's why you have to divide by 2. Okay, or you could think about number of bonds, okay? So think about carbon dioxide, our first symmetrical Lewis structure that we wrote, first symmetrical resonance structure. That was right like that. How do we calculate the formal charge? You're going to calculate the formal charge for each atom. Okay, so if we did oxygen, well, both the oxygens are the same. Hopefully you can see that, right? They both have a double bond and they both have 2 electrons. So the answer is going to be the same. They're the same type of oxygen. And intrinsically, the number of valence electrons to any oxygen atom is 6. We're going to subtract 4. So these two lone pairs in red, we're going to subtract that. That's the number of non-bonding electrons, not number of lone pairs. Number of non-bonding electrons is 4. 1, 2, 3, 4. And then we're going to subtract the number of bonding electrons divided by 2. There's 4 bonding electrons. So we divide by 2 and we get 2. Or you can think about it as there's 2 bonds here, so you subtract 2. Either way. And so 6 minus 4 minus 2 is 0. So the formal charge on that is 0. Now do the formal charge on carbon, right? Well, carbon has 4 valence electrons, and it doesn't have any lone pairs here, so no non-bonding electrons, minus 0. And it has 4 bonds, or 8 bonding electrons divided by 2, right? 2, 4, 6, 8 divided by 2 gets you 4. So 4 minus 0 minus 4 is 0. So the formal charge on all these atoms is 0, okay? And so, we were going to practice this one here. Let's just do that now. So this is one of our other Lewis structures, okay? And so here's oxygen number 1. Here's oxygen number 2. Why don't we just do carbon as well? We might as well since we're here, okay? So there's a formula for formal charge. Here's oxygen. So oxygen is going to be 6 valence electrons minus now the number of bonding electrons is 2, 4, 6, minus 6. And then I'm going to number bonding, non-bonding electrons is 6. Number of bonding electrons divided by 2. Let's just say divided by 2. Okay, divided by 2. There's 1 bond, 2 bonding electrons. So 2 divided by 2 is 1. Okay, so our answer there is going to be equal to -1. Okay, so we know the answer here is going to be C or D. This is oxygen number 1 we're talking about. Let's do the other oxygen here. Oxygen again was 6 valence electrons minus, we are, how many bonds here? 2, 4, 6 bonding electrons divided by 2. Oops, I'm getting ahead of myself. How many non-bonding electrons? 2, right? 1 lone pair, 2. So minus 2. And now we can ask bonding electrons divided by 2. 2, 4, 6. 6 bonding electrons. 6 divided by 2 is 3, or 3 bonds. It's a triple bond. Okay. And so our answer there, 6 minus 2 minus 3 is 1, positive 1. So our answer is going to be C here. Okay. Let's just for practice do carbon also. Carbon has 4 valence electrons. Minus 1, 2, 3, 4. No, minus non-bonding electrons. There's no lone pairs. Minus 0. Okay. And then minus, how many bonding electrons are there? There's 2, 4, 6, 8. Divide by 2, that's 4. So that gets us 0. All right. So that's how to calculate formal charges. All right. And so once you have that, here's some rules for knowing whether or not knowing what resonance structure to choose. Okay. So now that you know how to calculate formal charges, how are you going to actually use them? And this is how. Okay. So you're going to use them. Basically, you're going to look for, I'll write this in the next video, but you're going to look for formal charges that are closest to 0. Okay. So like in our previous example here, this one had all zeros across the board. And so that was very good. Both oxygens have 0, carbons have 0. So that's a very, indicating to you it's very stable. So closer to 0, the better. Okay. Smallest numbers, the better. Closest to 0. Okay. And if you have to have negatives or positives, you want the negatives to be on the more electronegative atoms, right? Because those are the ones that want the minus charges. They want the electrons. And you want the positives to be on the least electronegative atoms, or the more electropositive atoms. So I'll write that on the next video, but that's the general idea.